Welcome back, everybody, and welcome to a new session on this course on machine learning. And the topic this week is actually to get started with a classification problem. And we're going to stay with the regression type of philosophy, and we're going to use this as a kind of stepping stone towards deep learning methods. Now, logistic regression, as you can also see in the slides here in the Jupyter Notebook, is a method which leads to equations when we are optimizing the parameters, where the equations have to be solved numerically, which means that that leads us into the topic of optimization problems. And these optimization problems are typically solved in terms of us calculating the gradient of the cost function or loss function. And then with these gradients, which we want to drive to zero, and later, as you will see with neural networks, we are going to use the gradients to train the parameters of a neural network. Then we need to confront the fact that we have to deal with these gradients in the optimization problem. And this leads to the family of gradient methods, from plain gradient descent, as it's called, to stochastic gradient descents, and all the variants of that. So we are going to use logistic regression not only to present a way to perform a classification problem, but also as a stepping stone towards gradient methods, which then are methods which we will need when we are setting up our neural network code. So when we studied linear regression with ridge regression and ordinary least squares, as we did in the previous weeks, we ended up with analytical expressions for the unknown parameters. And the only thing we needed to do then numerically was to invert a matrix. And there we have pretty reliable algorithms for performing the matrix inversions. Except for lasso, which we have to resort to iterative solvers for finding the optimal parameters, for ridge and ordinary least squares, we could play around with different analytical solutions. We could study the variance of the parameters beta. We could find the expectation values of the different parameters, and we could even use a statistical analysis in order to derive the same equations, which we could obtain from plain linear algebra. Now, concerning practicalities, the material which you see here is also a material which we will use when we meet next week. So next week, we will have a session on Sunday in the afternoon, and most likely we will start at 2 o'clock, and I'm going to send you an email when we start and where we will meet. And then we will have a regular session plus project work till noon on Monday. Now, I will also then present to you the first project, and this is something which we can discuss a little bit more together so that we can try to streamline it towards your scientific interests. Last year, this was extremely successful because we had several groups which were working on their own data, and then they wanted to use this data in the analysis with machine learning methods. And we could really tailor the kind of data sets to people's individual needs. But we can discuss this in more detail when we meet on Sunday and on Monday this coming week. So you will get an email later this week with the practicalities of where and when we will meet on Sunday. And then the same applies to Monday as well. And the aim is then not only to summarize what we have done, but also to point to what can be done in Project 1. Now, some of you last year did actually combine Project 1 and Project 2 with different methods and just turn in one single project where one used both deep learning methods and regression methods to analyze a data set. These are also things which we can discuss in more detail when we meet. So feel free if you have any questions about the topics for the coming weekend and next Monday. So we are going to use the lecture today more to prepare the material for what is going to come. And the slides which you see now for this specific session are slides which we will continue with on Sunday and Monday, the 12th and 13th, respectively. So as we say here, classification problems. Till now, what we have done is to try to fit a continuous function. However, when we fit a continuous function, this is less adapted for us doing a classification problem. So the most common case of a classification problem is a typical true-false case, normally what we call a binary classification problem. So we would typically have two classes. One of the data sets which we're going to encounter is a famous one, which has been used in many, many machine learning applications, and it's called the Wisconsin breast cancer data set. And this data set has some data about 500 plus patients. And what they've done is to classify whether a tumor is a benign one or it's not a benign one, which means that you have a typical true-false case, which you normally convert into numerics. And in the numerical representation is like 0 and 1, -1 and 1, just a binary case. So this is one of the most common cases, and that's the one we will focus on in the lecture here today. But we will also mention the case where you have other kind of output types. So this could be 3 types of outputs, it could be 10 types of outputs, and we are going to call these categories or classes interchangeably. So one typical example of more than just 2 types of output is the so-called MNIST dataset of handwritten numbers from 0 to 9. So that means that you have 10 categories or classes, the numbers 0, 1, 2, 3 up to 9. And then you get something like thousands and thousands of handwritten numbers. And then you train a network to classify correctly whether this is a number 1 or number 2, etc., etc. So that would be an example of more than just the binary case. So when we deal with the optimization now, logistic regression, as we write here, is something which will serve as a stepping stone. Actually, logistic regression is a very simple way to perform a classification, and it contains many of the basic philosophies which we also encounter for classification problems, not only in deep learning methods, but also in other methods like support vector machines, or if we are doing random forest, decision trees, etc. So many of the things which we are going to touch upon here now, the problems with derivatives, which lead to expressions for the optimal parameters, which are not simple analytical ones, is also something which we will encounter when we deal with deep learning models, and in particular if we're dealing with the convolution neural networks or neural networks, etc., etc. And that's something which we will start discussing in the second half of November and for the rest of the semester. So the semester is going to be split between classical methods like these ones, what we normally dub the pre-deep learning revolution methods, and then we're going to look at the deep learning methods like neural networks, convolution neural networks, and then recurrent neural networks. And that will roughly define what we will cover in total here. So the typical cases which we are going to deal with is a set of classes of outcomes, which we have labeled as a Y of I. We can also call this for target values or outputs, etc. And we could have a series of classes. And the goal is actually to predict the output classes from the design matrix, as before. So the design matrix, if you think of this cancer data, then the design matrix is a system which now contains along the rows, the data entries. So for the cancer data, this could be the number of patients which have been surveyed. And then in the columns of this design matrix, we could have the features of the tumors. And typically for this Wisconsin breast cancer data, there's something like 30 features. And one of the features could be the thickness of the tumor. Another one is the circumference of the tumor. Another one could be the radius of the tumor. And some of these data are obviously correlated. And you will then have something like 30 ways to classify a tumor. And the pathologists are normally pretty well trained on this, and they can see from these different parameters whether this is a benign tumor or whether something more serious is happening. Another data set would be is a famous one on credit card users, and that could default or not on their credit card debt. That's also an example of a binary outcome where you have yes or no on whether you default or not on your credit card debt. So what we are going to look at now is a quick reminder first of what we've been doing till now, and then we are going to look at the difference between the standard linear regression case and a classification problem. Just one thing I wanted to say a little bit before we move on to the whiteboard. Here is a simple example of some very simple data set on coronary heart disease as a function of age. So this is a typical binary classification problem. So you can classify whether the person has had a coronary heart disease with output 1 or not as output 0. And this output is plotted against the person's age. If you now look at this specific data set, you would now see something like this when we display everything. So you would have a different age group from 20 to 24, 25 to 29, etc., etc. And you see the ages of the different patients. There's a survey of 100 patients here. And then when you look at the distribution here of the data, clearly we could now, if we want to, we could fit a straight line which just goes in between the two results and just separates the two classes. Or we could actually just draw a line and see if we could predict whether this person has had coronary heart disease or not. But you see now that this is not perhaps the best approach. That means to use our standard linear regression case to try to fit this data set here. And this is where logistic regression comes in. So you see very clearly here that making a fit, a polynomial fit, for instance, is perhaps not the best recipe. So you can see now that there are less people at low age which may have a coronary heart disease, whereas when you increase the age, it's more likely that you will have more people with a coronary heart disease. Now, one thing, and this is something which is going to suggest how we could interpret this data. If you now take the mean value for each age group, then you would get something which looks like this. So this has, if we're putting a goodwill into it, it looks like an S-shaped function. So what we are going to do now, instead of making a linear regression fit to the data set which we want to reproduce, we are now going to replace our continuous function with a probability distribution. And this is going to give us a model which we then can use to set up a different cost function with respect to what we did before. So after these preliminary words, let's now just take a closer look at the mathematics which is needed to set up logistic regression. So logistic regression, before we do this, is one of the simplest ways of performing a classification problem. And before the deep learning revolution, this was a kind of method of choice almost. And you will find many scientific articles where one uses logistic regression to perform a classification task. Any questions so far? Okay, so let's now switch over to the whiteboard. Okay, so if we now think of the classification problem and logistic regression, so a typical situation which we will have now is something which looks like this. So we will have some data set X here, and then we have an output. And the output would typically be distinguished between two outcomes. So this is a binary case. So we would have a 0 and a 1. So let's just look at the binary case, because that's the one which is easiest to interpret. And then we would have some observations like this. And we could have something like here. So, and a series of such observations. So one thing we could do now is that we would still insist on our linear regression case, since we got so convinced that this is something which is very useful. So if you use it, if you look at linear regression, what we have then is a function y of I, which is typically defined, approximated by a sum over all these parameters in the design matrix multiplied with the unknown parameters, plus some randomly distributed noise. And as we discussed last week and the weeks before, this random noise is typically something which follows a normal distribution with zero mean and a specific standard deviation and variance, sigma squared. So what we have assumed then is that this continuous function, j of x or f of x, beta j, this approximates a continuous function f of x of I. And we have also assumed that y of I, so we should put an approximation sign here. So y of I is given now by this function fx of I, which we don't know. And this function is assumed to be a continuous function. And it's also assumed to be a non-stochastic function. Now, one of the things which we could do now, we could obviously enforce a linear regression fit to the data. And then we could fit a line which goes something like this. If we are insisting on a linear fit with a first order polynomial, we could try to fit a second order, higher order polynomial, and perhaps that would be something which could go through most of the data points, something like this. But this is not very useful actually, because the function f of x, which we're trying to fit, it takes in principle values from minus infinity to plus infinity. So if we look at x here, this is a variable which is defined between minus infinity and plus infinity. And also y, when we look at the continuous function, y would be a variable which goes from minus infinity to plus infinity if it's a continuous function. However, in our case, y is only given by 0 and 1. So we could definitely fit a line. We could fit another line which separates the two classes here. And we could say now that if the value is larger than a specific threshold, then we would say that, okay, if it's larger than a specific threshold, we put the output to 1. And if it's below a specific threshold, we put it to 0. So that's one possible way by which we could now insist on using our linear regression case and simply fit a function where the function is given by a straight line, and that straight line separates the two classes. Now, again, this is not very useful because we are then assuming that the function f of x is a function which in principle takes values from minus infinity to plus infinity, whereas we wanted to take values which are confined by 0 and 1. So what we are going to do now is actually to replace this function f of x with a probability distribution. So let's just switch this whiteboard page here. So what we have assumed till now in linear regression what we have is that y of I in principle is a variable which can take values from minus infinity to plus infinity. It can be constrained by another interval. And the same applies to x of I, goes from minus infinity to plus infinity. So this is a standard approach which we have seen till now. But in logistic regression, what we want this function f of x to represent is more a set of discrete outputs. So in logistic regression and classification problems, what we want now is that this y of I we want this function f of x of I to represent discrete outputs. So what we want now is that in the case of a binary, if we take that as an example, what we want then, since y of I then is given by two values, 0 and 1, then we would like this function f of x to behave in the same way. So what we want then is that f of x of I moves over to a p of x of I, which we will simply label as a p of I here. And the simplest case which we have now is a function which is called a sigmoid function. So one of the absolutely simplest one is this function here, and that's given by e of a parameter beta 0 as before, and a beta 1 multiplied with x of I divided by 1 plus e of beta 0 plus beta 1 of x of I. And this is often rewritten in terms of a simpler function of 1 plus e of minus beta 0 minus beta 1 times x of I. This is just a case where we have one feature, and it mimics a little bit of what we did in linear regression with a straight line, where we had parameters beta 0 and beta 1. This function here is normally called a logistic function or just a sigmoid function. And it has some interesting properties that this function here, when we let x of I go to minus or plus infinities, it approaches either 0 or 1. And you can see that immediately when I let x go to minus infinity or I let it go to plus infinity, you will then see that the limits are either 1 or 0. So this function has the kind of properties which we would like to have if you go back to this data on coronary heart disease. So if I make a plot now of x, and this function, so if we have 0 here, and then we have 1 here, and the type of output which we are having could look something like this. We could have a set of observations here, etc. And we could have a negative value for the x's as well. So the function which we are plotting now, the sigma of x, is a function which is going towards infinity to 0 when we go from minus infinity. And then we are going to have, just a moment, I want to draw this in red. And this takes up like this and goes like this. This is very schematic. And then this is a value of a half at 0. And what we could say now is that if this function p of x, which is given by this sigma of x of 1 plus e of minus x, if that function, if p of x is larger than 0.5, then we output, then y output of a model is equal to 1. And if this p of x is smaller or less than 0.5, what we would output then would be just 0 here. So that's just one simple way of producing an output, which we can compare with the experimental data which we have. So one thing which you will notice with this specific function we have now, this p of x, is that you can normalize it over the domain of all events x, of all the stochastic variables x. X doesn't need to be a stochastic variable, by the way. But in this case, we're assuming that we can treat it like a kind of stochastic variable. And you can actually normalize this function to 1. And this is fully possible. You just need to calculate the normalization integral. And that will give you a constant in front of the function value. So the basic assumption which we are making now is the following. So our assumption is that the data which we are looking after, this y of x, is now defined by this probability p of x plus some noise, which we still don't know what it is like. So we haven't made a model for the noise. And you remember that when we did linear regression, we assumed that the noise followed a normal distribution. Now, in our case, the noise is not going to follow a normal distribution. So what we have is a model for the probability. And this probability is then given by the sigmoid function, which is simply E, and then we have the argument P beta 0, which is an unknown parameter, divided by 1 plus E of beta 0 plus beta 1 times x. So this is the model which we are making. Now, in principle, what we have is a domain of events, and these are given by x0, y0, x1, y1, etc. So given a set of x's, we get a specific output up to the final data entries. And this could be, for instance, if we're looking at this cancer data, the x's could be the given patients and the features which we encode for the cancer data. So as I said, these cancer data have something like 30 features. So it means that you will not only have a beta 1 here, but there will be a beta 2, a beta 3, etc. So now we are just looking at this from a very simple way with just two unknown parameters. But keep in mind that in principle, so let's just put that as an aside, this beta of x could actually now be given by a beta 0, there could be a beta 1 of x, there could be a beta 2 of x, etc. And that depends on the number of parameters which we have. And in this case, the x's would then refer to the specific parameter. So you could think of now the beta 1 in the tumor data. Beta 1 could be related to the thickness of the tumor. Beta 2 could be related to the radius of the tumor, and so on. So we can then generalize this to many more parameters, as we did before. And we keep still this kind of linear dependence. We can make this dependence nonlinear, but that would complicate the argument to the function, to the exponential function which we have here. So let's keep things simple, and we are just going to look at the binary case with a simple model for the probability distribution, and this is going to be given by the sigmoid function. Now, just to remind you of some other possibilities, there are many ways by which you can approximate this kind of function. So if you go back to the Jupyter notebook and take a look at that one, what you will see is a set of functions which are used in the literature. So the logistic function is one of them, or just a sigmoid. It has the nice property that we have a classification problem with two events. So that means that there is a probability for one of them, which we simply call P of t. And then there is the other one, which is just 1 minus P of t here. Now, if we now look at the following function which we have here, there are examples of possible probability distributions of functions which we can use as probability distribution. And one of them is the sigmoid, as we called it. Another one is just a plain step function. And if we plot them, you see now that the sigmoid function, when z here, the argument goes to minus infinity, it goes towards 0. And when c goes to plus infinity, it goes towards 1. And then we have a centered around 0. It just gives us a value of a half. Another function is a step function. But there is a reason why we don't use the step function. And one of the main reasons for not using the step function is that its derivative, and this becomes important when we are looking at deep learning methods, the derivative is discontinuous. So it means that we have a discontinuity at 0 here. And this is something which is not wanted, because when we are training a neural network, we would like to have functions which have at least continuous derivatives. And that makes it much easier when we now are going to implement things numerically, because if you have a discontinuity, we have to plug in an if test, and also the function is not defined at c equal to 0. Another function which is widely used, actually more used than the sigmoid function in deep learning methods, is a tanh function. Now, anyway, we, in our derivations here of the logistic regression, we are going to stay with the standard approach, which starts with this sigmoid function. But keep in mind now that this sigmoid function is just one of many functions which can now be defined, can be used to define a probability distribution. So let's go back to the whiteboard now. So what we have is a function which we are going to interpret as a probability distribution. And in our case now, with the domain which we have defined, so what we have is a probability distribution, which we are going to define now as follows. So I'm going to define a probability of x, which I change to a probability for given event y of I. And this is with a given x. So with y of I equal to 1, then I also have an input x of I. And this is going to be a function of the parameters beta. So this is the single probability. And this is simply given by this probability E of beta 0 plus beta 1 times x of I divided by 1 plus E of beta 0 plus beta 1 times x of I. And we will also, in the coming equations, we will also just relabel this as a P of I. So that P of I there stands for the outcome equal to 1, or the output, or the target value, as we will also call them. Now, so this is one of the cases. And then we have the other case where we have a P of y of I equal to 0, and with an argument x of I with the parameters beta. And that has simply to be given by 1 minus P of I, because we have only two probabilities. And the sum of the probabilities, as you can see here, so we have the possibilities of I equals 0 and 1, and then we have the P of y of I with a given x of I, and now I skip the beta here, that is equal to 1, as it should be, when we sum over all the possible events which we have. And you see now that in one case I have P of I, and the other case I have 1 minus P of I, and that simply sums up to 1. Now, one of the things which we're going to do now is to assume the following. So this is an important assumption about the data which we have. So we are going to assume that the probabilities for y, so that y of I, are so-called independent, and identically distributed This is the same approximation which we made for linear regression. Distributed. This is normally shortened to IID, as we discussed last week, in connection with the statistical interpretation of region lasso regression. So that means that we can now, if we take this domain which we have, this domain D, we can now define a probability which is just a product of all the single probabilities. So what we could say now is that this P of D of beta is now given by the product of all these individual probabilities for the different y's. So this is a probability of finding this set of y values for the whole domain of input variables and output variables with a given set of parameters. So this is something which we now assume is given by this set of probabilities with a given beta value here. So this bar means that what is the probability of finding y of I with a given x of I, given that we have a parameter beta. And it means that when we now are setting up these probabilities, we need to figure out what kind of probability distribution we should use for this piece. So we have assumed this binary distribution here. And one of the ways by which we can extract some information is to find out which kind of probability the parameters epsilon are following. So let's now ask the question here, because x is assumed still now to be a non-stochastic variable. So what probability distribution does the noise epsilon follow? So we can now set up these epsilons, because what we have is a model which we have made, and it's pretty straightforward to do this. So we have assumed now that for y of I, the output equal to 1, this is the same as p of I plus this epsilon of I. So that means clearly that epsilon of I has to be equal, since y of I is 1, then we have 1 minus this p of I. If I take y of I equal to 0, then we see immediately that this epsilon of I is simply equal to minus p of I. So these are the values which we have for the epsilons, and then we can calculate the expectation value of the epsilons given this probability. So we know the probability and we know the values of epsilons. So what we can do now, since we have only 2 events, so we can now set up, and now I'm going to use a further shorthand notation. So I'm going to let the p of I simply be represented by the letter p. This is just a shorthand notation. So if I do that, if I want to calculate this quantity, I have a sum over all the possible events which I have, and then I have epsilon of I of 1 of p of I here, which in our case is now defined by the different probabilities. So what we have now is, in the first case, when since we only have 2 outputs, so we have epsilon equal to 1 minus p, and that has a probability of p, because that's the case which we put up here. This is this one, and that has probability p. And then we have the case when we have y of I equal to 0, and in that case we have minus p for epsilon, and this is multiplied with the probability, which is 1 minus p. So we are simply using the definitions for the probabilities, and we are trying to calculate the mean value of epsilon. So what we see now is that this simply sums up to 0. Then I can try to calculate the variance of epsilon, and then I just repeat the same exercise, because now I have a mean value for epsilon, which is 0, which means that now I have 1 minus p, which is epsilon squared, times a probability, and then I have plus, and then I have minus p squared, multiplied with the probability. So this is the definition of the variance with a mean squared value equal to 0. We don't need to account for that one. And that gives us p of 1 minus p. Now, this is a quantity which we now recognize as the variance for the binomial distribution. So epsilon follows a binomial distribution. With variance, which is given by p of 1 minus p and mean value 0. So that has with mean value 0 and variance of p of 1 minus p. And that is something which we will now use when we are going to set up the probability distribution for the total set of events which we have. So we have assumed now that x is not a stochastic variable. The epsilon values follow a binomial distribution. So that means that the y's which we have should also follow a binomial distribution. And the way which we are going to do this now is simply to assume that we have a probability distribution of p for the whole domain with the given parameters beta, which are going to be given by these simple probabilities which we set up. So we have a product of all the probabilities up to n minus 1. They are assumed to be identical and identically distributed and independent variables. So I have a P of I, and this contains now Y of I to the power of Y of I. And keep in mind that Y of I can be 0, 1. And then we have 1 minus P of I multiplied with, to the power of Y, 1 minus Y of I. So this is a model which we are making. And you see now that in case Y of I is equal to 1, then this equation here simply gives us P of I, the sigmoid function, which we assumed. And if Y of I is equal to 0, this becomes 1. And then I have 1 minus P of I here to the power of 1. So this is just a very simple way by which we can now set up the function we want to optimize. So what we would like to do now is simply to use a principle which is called the maximum likelihood estimation. So what you have now is a probability or likelihood. And we want to find the parameters beta which maximize the probability. So this is normally called the maximum likelihood estimation. And the parameters beta become then the maximum likelihood estimators or the maximum likelihood parameters. So you will often see this shortened to an MLE in the statistics literature. So what we want then is to find the parameters beta which maximize the probability distribution. Clearly, we are not interested in a parameter beta which minimizes the probability. That should be pretty obvious. So what we want now is to find an optimal parameter beta which, with a given argument, arg, max, and then we, oops, sorry, I just had a small. So we want to maximize that for the different parameters beta in our data set of Rn. This has dimensionality P. So the design matrix is as before. It has a dimensionality number of entries N times number of features P. And we want now to optimize this function here. So this function, however, is actually a little bit more tricky to optimize, because when we look at the derivative of that function, so the cost function now, or loss function, or our optimization function, the cost function is actually given by this probability distribution of d of beta. So what we want when we want to find these parameters is obviously to find the gradients of beta, and we want to drive that to 0. Now, to perform that operation on the product is actually not that easy. So an equivalent problem is actually to optimize the log of the probability, which is numerically or analytically easier equivalent problem, as we discussed previously in connection with linear regression. So if you go back to the lectures we had last week with the statistical interpretation and also the week before. So equivalent problem is actually to optimize. So beta is equal to argmax of beta here. And we optimize log of P of d beta. Now, we can optimize or maximize the problem, or we can minimize. So suppose now we want to insist on this minimization problem. So we could then, or we could simply find that the optimal parameters beta are given by the minimization, because the log function is either continuously rising function or continuously decreasing if you have a minus sign. So we could actually take the minus log of this probability distribution. So this is the basic mathematical recipe which we are going to use now. So that means that if I now take the log of this function here, what I end up with then is that if I take the last one, this means that my cost function, the function I want to optimize, is going to be given by minus And then instead of the product, I have a sum over all the logs here. So I would have an I equals 0 up to an n minus 1. And then I would get a sum here, which runs like y of I of log of p of I. So this is the probability of which our model is giving us. Y of I is the output we want to reproduce. And then I have plus an I minus y of I. And then log of 1 minus this quantity p of I, which is now given by our model for the probability, where p of I is simply e to the, with argument beta 0, beta 1 times x of I, with 1 plus e of beta 0 plus beta 1 multiplied with x of I. And if we plug that one in, then we have the expression which we are going to calculate the derivative of after the break. So if I do that, then I can simply plug this in. So if we just put a parenthesis here, then we would have a minus, and I have a sum of I equals 0 up to n minus 1. And I get a y of I. And then since I'm taking the log of this exponential here, I get a beta 0 plus a beta 1 times x of I. I will have a denominator, but that denominator is something which disappears when I look at the next term. So what I'm going to get now is minus, and then I have log of 1 plus e of beta of x beta plus beta 1 times x of I. So this is the function I want to calculate the derivative of, and we are going to do that after the break here. So if I now look at these expressions here, these are the kind of expressions which we will now manipulate in order to find the derivatives. And what we need now after the break is actually to calculate the quantities you see here with this new cost function. So what we did was to assume that we have independent and identically distributed stochastic variables. These identically distributed and independent variables give us a probability distribution, which is just a product of all the individual probabilities. And instead of taking the derivative of a product, we rewrite that one in terms of the derivative of a log or minus a log. So the cost function is normally defined in terms of the log of the probability distribution. This function, which you see here, has a name in the literature, and the name which you will encounter for this specific function here is, so this one, the one which we have here, this is normally called the cross entropy. And it's a widely used cost function for classification problems. Now, after the break, we are going to calculate the derivatives with respect to the unknown parameters. And then with these derivatives, we are going to find the optimal parameters. And with that, we are ready basically to start discussing these gradient methods. So the logistic regression serves as a kind of stepping stones towards the methods which we encounter in deep learning and neural networks, and also the different gradient methods, because the optimal parameters beta, when we take the gradients, they will not give us nice analytical expressions. For the break, we derived the so-called cross entropy, which is just a model for the cost function, which can be used in classification problems. And we made an assumption about the probability which governs the outputs. So we found with this simple binary case that the kind of probability distribution for the noise, which we previously in linear regression used a Gaussian distribution with zero mean value, we have now a binomial distribution with zero mean value. And that leads to a model for the total probability, which is the probability, the multi-product of all the individual probabilities, since we assume that both the noise and the output which we have are given by independent and identically distributed variables, stochastic variables, then we could construct a model where we have a cost function now, which is when we take the log of the probability, we get a function whose dependence on beta we are going to use to find the gradients. So let's now take a look at the calculation of the gradients here, because what we want is now to calculate the gradients and drive these to zero. And that is going to provide us with the optimal parameters, which either maximize or minimize the log of the probabilities. So essentially what we have done is very, very similar to what we did when we set up the equation for linear regression. So the first thing we can do now is simply to calculate the derivatives. And if we do that, we find, we now just repeat the equation for the cost function. So we have a C of beta, which depends now in our case only on two parameters. So we have a sum from I equals 0 to n minus 1. And we have this y of I, which is the output. This is multiplied with beta 0 plus beta 1 of x of I. And then we have a minus, and then we have log of 1 plus e of beta 0 plus beta 1 of x of I. So when we now are going to calculate the gradients here, we need to calculate the gradients with respect to beta 0 and with respect to beta 1, and we want to drive these individual ones to 0. Now, what you would see now when we calculate these quantities is that this quantity becomes minus, and then I have a sum from I equals 0 up to n minus 1, and I'm going to get y of I minus p of I. And just to give you an intermediate calculation, if I take log of 1 plus e of beta plus beta 1 of x of I, and derivative with respect to beta 0, we know that this one is just e to beta 0 plus beta 1 x of I divided by 1 plus e of beta 0 plus beta 1 x of I. And then we see that when we take that derivative, this is nothing but the quantity p of I. And we obtain then the function, which now depends on the difference between the target value we want to reproduce, y. So this is fixed. This is just the output from a given experiment or a given survey, like this cancer data, which we discussed before the break. And then p of I is what our model produces. And I'm going to call this for a G0. So this is a derivative with respect to beta 0. And then I need a similar one with respect to beta 1 here. And we want that to be equal to 0. And it shouldn't come as a surprise that we get a similarly simple formula. So this is going to give by n, given by n minus 1, sum up to that, and then a y of I minus p of I here. So this is the equation. These are the equations for the two derivatives. I'm going to call this for G1, gradient 1 and gradient 0. In general, what we get is the following. And I'm just going to list up the equations here, and I'm going to leave that as a small exercise for you guys. So the general equation, if I now rewrite this in terms of a vector beta, so I have a derivative with respect to the vector beta. So this is a derivative of scalar with respect to a vector. So that has to produce a vector. And what we can show is that this is equal to the transposed design matrix. I have a minus here and a y minus p. And we can rewrite that one as an x transpose of p minus y. So that would be the gradient which we have. And if you now look at the dimensionalities, we remember that x transpose has now a dimensionality of p times n. And we know that y and p are probabilities, so they have defined by a vector of length n. So what we do now is that when we perform the calculations here, you see that we have a matrix of dimensionality p times n, which is multiplied with a vector of length n. So that gives us a new vector of length p. And we are going just to call this for the gradient. When I don't define arrows and things like that, it should come from the context whether this is a vector or a scalar. So g is a vector and c is a scalar. The cost function is a scalar, has to be, if you think of the mean squared error. So we see now that g is now a vector which is defined by the features which we have. And the features reflect the parameters we want to find. Now, there is another quantity which I will also leave as a small exercise, as we did in connection with linear regression. And this is the derivative of the gradient, which now defines the so-called Hessian matrix. And this is given by the derivative of the parameters beta. So this gives us the Hessian matrix, which we labeled with an H. And that is given by X transpose times a matrix W. And this matrix W takes only diagonal values. So W is equal to a probability P of I multiplied with 1 times 1 minus P of I in case of I is equal to J for the matrix elements. And then I have that my matrix elements Wij are equal to 0. So this is Wii. And this is equal to when I is not equal to J. And the gradient then is now given by this X transpose times P minus Y. And then I have the Hessian matrix here. These are the equations which we now are going to use when we are going to find the algorithm for setting up the parameters beta. Now, what I want you to pay attention to now is the following. So if you think back to linear regression, and if we look at just ordinary least squares of OLS, what we found then was that the parameters beta are given by the X transpose times X, the inverse of that matrix times X multiplied with Y. Now, the thing is now that if we look a little bit closer into the expression for P here, so Y does not depend on beta and X does not depend on beta. So let's emphasize that. So if we take the gradient G, which is given by X transpose times P minus Y, what we see here is that, and this is the quantity we want to drive to 0, this has no beta dependence. And this applies to Y as well. They do not depend on beta explicitly. P, on the other hand, is a function which depends on beta, but now it depends on beta in a nonlinear way. So we would have the exponential here, and then we have beta 0 plus beta 1 times X divided by 1 plus the exponential of beta 0 plus beta 1 for this simple model here. So we have a nonlinear dependence on beta, which means again that we cannot find a nice, unless we are very, very lucky, we cannot find a nice analytical expression for beta, like we did in linear regression. So this means that we have to solve these equations numerically. So what comes out of this simple analysis of the equation is that we have no analytical solution. Remember that even if we had an analytical solution, we had to solve the equations numerically because we needed to invert the matrix for ordinary least squares. But we have no analytical solution. For beta, due to the fact that we have a nonlinear dependence on the parameters. And that means that we have to solve this numerically. Numerical solutions are needed. And the standard method for solving these type of equations is given by a so-called Newton-Raphson scheme, which is an iterative scheme. And we are going to derive that one by looking at a simple Taylor expansion of the cost function. So we need numerical solutions. Using iterative schemes like Newton-Raphson. And I assume that you may have heard about this scheme, but I'm going to repeat it for you now. So how can we derive this scheme? Now, what we are going to assume now is that we can Taylor expand the cost function around an optimal parameter beta. So to show this, we will Taylor expand C beta around the optimal value. And beta hat is the optimal value, which we find when we have reached the minimum or where the gradient is equal to 0. Now, there's another interesting thing before we move on now. The Hessian function, this second derivative, is a function which is a function or matrix which has eigenvalues which can be 0 or larger than 0. So the Hessian matrix is a semi-positive definite matrix, which again means that for this logistic regression case, we have a convex optimization problem. But let's now look at the Taylor expansion of the optimal parameters. So we are going to expand this beta around a value which I'm going to call for beta of n, which is going to be the result from iteration number n. So we are going to find an iterative solution based on this Taylor expansion. Now we're just saying that we are expanding beta around a specific value, and that beta of n is pretty close to the optimal value. So what we have then, when we Taylor expand here, we have a C beta optimal, which is then obviously, if we're just using the recipes for Taylor expansion, this should now, and we have to be a little bit careful because these are no longer scalars, but they're actually vectors. So I'm going to have the gradient, and the gradient is evaluated at iteration n because the gradient depends on the value of beta. And this is a transpose vector, and this is multiplied with beta, which is a vector. Just keep that in mind. So this is a scalar because it's an inner product between the gradient and the difference, which we are looking at. So the next term is then given by 1/2. And I have to be a little bit careful because I need now to consider both a matrix and a vector. So this is transpose, and this is now multiplied with a Hessian matrix, which depends on the value of beta. This is a second derivative. So just remember now that the Hessian matrix is the second derivative. So we are doing a Taylor expansion now, and we are not dealing with scalars only, but we have vectors and matrices. And that means that we have to be a little bit careful with the sequence of operations here. And then we have the next case, which is a beta minus a beta of n here. And then we have higher order terms, plus, plus, plus. Now, what is pretty common now is to truncate the Taylor expansion at the order of the second derivative. So this in itself is an approximation. And you will be surprised to see that this is the basic approximation for finding the optimal parameters, whatever kind of method you're using in deep learning or standard methods like logistic regression, support vector machines, or any other machine learning algorithm. That assumes that we can Taylor expand the function, the cost function, which we want to optimize, and we truncate it, the series expansions at the level of the second derivative. So just let me also remind you that dc d beta is evaluated at the beta of n. And that is the same as this gradient which we defined of g is actually minus the gradient of g of n. And then we have the second derivative is also evaluated at the value beta of n. And this is given by this Hessian matrix of n here. So I'm going to make a small replacement in the equation which you see here. So I'm going to introduce a new vector, which is just the optimal one, optimal parameter for beta minus the parameter which we are expanding around. So with the introduction of that one, what I end up with is a new function where I can now rewrite my cost function approximated to the second derivative. So I'm going to have an approximation here, and this is given by the cost function at this specific value plus my g of n transposed multiplied with a vector b plus 1/2 of b transposed times h of n times b. And now we stop at the second level of the second derivative. Now, this is the same as us making an assumption of a function f of x. And this is actually one of the starting points which you will find in many of these convex optimization problems. There is a basic assumption that there is some kind of a quantity gamma times an x. So gamma is a vector, and x is a quantity which now is defined to be the variable, the input to this function f of x. And then we would have plus 1/2 of x transpose times a, where a is a matrix of x. Now, this problem here is also a problem which has a famous solution, because if I take df with respect to x, what I'm going to get then is a standard linear algebra problem. So I can actually put a minus here. If I put that one equal to 0, this leads to a famous linear algebra problem, which many of you have seen before, where I have a gamma of t. Gamma is a vector, and a times x is now the a is a matrix which is known, and x is an unknown vector. And then we can find this solution here by simply solving this linear algebra problem. So this is actually this should be gamma as a function of gamma not transpose. So this is a pretty famous problem which many of you have encountered in linear algebra. And what we end up with now, with truncating at the level of the second derivative, when I take now the derivative of the cost function with respect to this quantity b, then this is going to be given by g of n plus the Hessian matrix multiplied with b. And we want this one to be equal to 0. So if we now remember that b is given by beta hat minus beta of n, what I have then is the following. So what I find then is that beta of beta hat is given by beta. And if I now assume that beta hat is given by iteration n plus 1, so I have performed n plus 1 iteration, and then the value doesn't change anymore, then I can just rewrite the equation which I have here as a beta of n minus, so we don't need a hat here because this is just the result from iteration n plus 1. So this will contain beta minus, and now I have the inverse of the matrix of beta, and this depends on the value n, and I have to take the inverse of this matrix, minus, and this is multiplied with the gradient calculated at beta of n. What you see here is nothing but the Newton-Raphson method. So this is the Newton-Raphson iterative scheme. But where we now are not trying to find the roots of a function f of x, but we're actually trying to find the roots of the gradient of the function f of x. So this is a Newton-Raphson iterative scheme. And typically this scheme would start with us setting up a guess for the value, and then we would continue and then find the final value after a series number of iterations. So what we've done now is actually to expand this in terms of a Taylor expansion. We've expanded the cost function, and then with this expansion we stop at the order of the second derivative, and this is actually what is normally done. So we are assuming that the difference between beta hat, the optimal value, and beta n is so small that we can neglect higher order terms. So what we have now, if we just rewrite this, what we are going to get then is the following expression. So we have a beta of n plus 1 when we now plug things in for logistic regression. We have h of beta of n, and this is inverse. And this is multiplied with, and now I have x transpose multiplied with p, which depends on beta of n. And this is given by minus of y. And finally, the final parenthesis. So you see now that where the bottleneck of all machine learning is, or the bottleneck of all this optimization problem is. So the bottleneck resides actually not only in calculating the gradient, but in calculating the second derivative. So the bottleneck of all optimization methods that resides in the calculations in h of beta of n and its inverse. And this is a quantity we typically want to avoid to calculate, or we would like to have a recipe which allows us to calculate this in a very easy way. So in neural networks and deep learning, in neural networks, it's very common that the number of parameters, it is common to have at least 10 to the 5 or more parameters. That means that the Hessian matrix, which we end up having to calculate in a deep learning method like a neural network. So this leads often to H having a dimensionality for some of the gradients of the order of 10 to the 5 or even larger, times 10 to the 5. So if you have 100,000 parameters, it means that you would need to do 100,000 calculations of the parameters. You may have something like 100 to 1,000 iterations before you hit the right parameters. And at every single stage, you have to calculate the inverse of this matrix here. So if your Hessian matrix is a matrix of dimensionality 100,000 times 100,000, then you have 100,000 parameters. So that means that you would have 100,000 rows down here, not only beta 0 and beta 1, as we saw in the slides, but we would have now 100,000 or more such rows with parameters. And if we perform 100 plus iterations, you have suddenly 100,000 times 100 evaluations. And in each stage, you need to calculate the Hessian matrix. And this has become simply an impossible task. So what is common to do then? And this leads to, how to say, all the evil of machine learning and the optimization problem. What is common then is actually to take this H, this matrix, and simply replace it in the first run with a constant. So replace with a constant. And this constant is often called the learning rate. So let's just rewrite the constant. We just label it with an eta. And this is the same as the learning rate. Now you can keep this learning rate constant, or you can find a recipe to update it with information about the gradients. And that leads to many, many different recipes. Some of them, the very, very simple ones, is called gradient descent with momentum, which is a very simple way. You can have a stochastic gradient descent when the matrices become very large and you don't want to calculate the full gradient. You can update this learning rate with iterative methods like adaptive gradients, which leads to a method called ADAGRAD. There is something which is called ADAM, and I mentioned to you in the beginning, so that's adaptive gradient with momentum. So these are all recipes which aim at trying to have some information about the gradients in the iterative process. So what we are going to do is actually to rewrite this equation, but now with a gamma here. So that means that when we are solving the equations, we will often have something which looks like this. So we have a beta, the optimal parameters after n plus 1 iterations, which is given by the previous value of beta of n. There's going to be a minus gamma, and this can depend on n, the iterations. And this is multiplied with a gradient at a given stage n. And this gamma of n, there are many, many ways of dealing with that. So we can have a constant value. We can have an adaptive value. So we have a method which is called ADAGRAD, adaptive gradients. We're coming back to that. There is something which is called root mean square propagation. There's something which is called ADAM, which is an adaptive gradient with momentum, etc., etc. There are tons of these methods. And in the beginning of the semester, I told you that a lot of the research in machine learning actually takes place around finding better optimization schemes. So this algorithm, which we have here, this ADAM, which we will discuss when we meet on Sunday and Monday, next weekend, this reference here has actually more than 10 to the 5 citations. It has actually 150,000 citations. And the paper came actually in 2014. So that's an impressive amount of citations. If you think that a good physics paper has typically 100 to 500 citations. So this tells you that if you're able to cook up something exciting here, you will get many, many friends. And I'm not inferring that you don't have friends, but these will be friends which will cite you, because this is a very, very active field of research. And we will discuss more about this when we meet on Sunday and next Monday. So a part of the project, or the second project, is actually us studying different gradient methods, because these are actually needed when we are going to train a neural network. So basically then, what we end up doing is to solve a set of equations which may contain some more detailed information about the Hessian, or may simply just run with a constant here. And this is the bottleneck of basically all machine learning. So we can get the gradients, but then we would like to avoid calculating this quantity here. Now, what I'm going to spend the rest of the time here, because we are not going to discuss the gradient methods today, but we are going to look at them at them in more detail when we meet during next Sunday and also next Monday. So I just wanted to mention that this is a very, very important topic in all of machine learning. So essentially what we have is 3 different main elements in a machine learning approach. So we have the data with inputs and outputs. We are making up a model, like we did here with a sigmoid function for the data which we want to reproduce. And when we have this model, we want to have a cost function where we can optimize and find the best parameters for the model, which reproduce the data we are looking at in the best possible way. So these are the basic 3 ingredients, but at the heart of all of these methods, what we have then is an optimization algorithm. And in some cases, we know that the function is convex. like the function we had for ordinary least squares and for Lasso and ridge regression. And the same happens with logistic regression. But when we come to a neural network with even millions of parameters, then we are not sure of what the function looks like, because it's almost impossible to plot it. So we may be stuck in a saddle point when we do the iterations. We can be in a local minimum, or if you're lucky, we may be in the global minimum. So this is life when we move into many parameters we want to tune. Okay, any questions so far? So this is the basic mathematics with all the inherent problems which we face when we do machine learning. And as I said, the big problem is us trying to find a way by which we can have information about the Hessian matrix. Keep in mind as well that these equations, which form the basis for a convex optimization problem, they are actually based on a Taylor expansion of the cost function around the optimal parameter beta hat. And we are assuming that the difference between beta hat and beta of n, the result after a given number of iterations, is very small, so that we can truncate the series expansion at the level of the second derivative. Okay, so I'm going to go back to the Jupyter notebook now and just perform some simple calculations. And so let's just bring that up. And down here, what you will find, if you just scroll down, first of all, you will find just a repeat of what we did in the slides. And besides this grid search and that stuff, what we have done here is actually to look at a specific data set, which is called the Wisconsin cancer data. So in this specific case, what we have is a data set which can be loaded into the algorithm by just using scikit-learn. So scikit-learn has this breast cancer data set, and this is a widely studied data set. So you will find many scientific articles. And in this specific case, instead of writing my own function, I'm using the functionality of scikit-learn. So I'm splitting my data into train and test, as we have discussed earlier. So this data set already sets everything in the format which we want to have. There is a design matrix X and the output Y. And then we can just split it by using the train test split functionality. And in this case here, if we just run the data set, what you would see now is that it has, for training, it has 426, and for test, it has 143, and it has 30 features. And these features are span from, as I mentioned earlier, things like the thickness of a tumor, the circumference of a tumor, the area of a tumor, etc., etc. And some of these quantities are correlated and some of them are less correlated. And in this specific case, I get a test set accuracy with logistic regression, which is 0.94. Ideally, I would like to have 1 here, because the accuracy is simply us counting the number of correctly classified events divided by the total number of events. So if you correctly classify everything, you have a 1 here, because then you have classified everything correctly. Now, in this specific case, and this is something which I will say a little bit more about next time, there is an algorithm here which is called LBFGS, which is a pseudo-Newton methods, and B stands, and F and G and S stand for the different authors. So this is called Linear, Broyden, I think Fagerberg or something like that. And I don't remember the acronym for the other authors, no, the names for the other authors. So this is a set of 4 authors which have developed a way to estimate the Hessian matrix in an iterative way without having to calculate the Hessian matrix. So the method which is used here is a quasi-Newton method, which we will discuss in more detail next week. Now, one of the things which is also interesting to do here is to plot the so-called correlation matrix. So if we do that, we can find which data sets are more correlated and not. So we can construct that using these panda statements, which you see here. And then we have the correlation matrix here, and you can now see when we plot it, we can see examples of how we can display the data for this data set. And you see we have a benign tumor, so the mean radius when it's typically less than 15, and this is a 15 millimeter. That's often a case of a benign one, but you see that you have a kind of area here where they overlap a little bit. This is, I don't know what all these things mean. Do you have the mean parameter, the mean area? These are some types of features which are known to pathologists when they classify the tumors. So I do understand what the mean radius is, but I don't know what many of these other parameters may actually mean. But these are the typical features which you will find in this data set. And then you can look at correlations here. And clearly, if you look at the mean perimeter and the mean area, which are these ones, and the mean radius, we would expect to have a high level of correlation, obviously, because the radius and the area, so the area will just be, has to be proportional with the radius. If you think of this as a circle, for instance. So there's a high degree of correlation between some of these parameters. And this is a very useful pre-analysis to make when you're looking at the data set. This simply tells you that many of the data which we have, they show strong degrees of correlations. We discussed the correlation matrix earlier. So along the diagonals, you have to have one. And the non-diagonal matrix elements are simply given by the covariance of the data divided by the variance of one of the variables times the other one, and then the square root of that quantity. So along the diagonal, you have just the variance of the mean radius divided by the variance of that specific quantity. And that means that you simply have then just one along the diagonals. And if you get one here, it means that the data set or the variables are strongly correlated. So if you continue now, if you look at this example, we display, in the first one, we display the overlap of benign and malignant tumors as functions of the various features. And we see that some of the features you can distinguish clearly, the different cases, while for the other features, there's a strong overlap, and you cannot make a clear statement. And in the second figure, you saw then the correlation matrix, which in this case is a 30 by 30 matrix. There are other ways to classify the data, and one of them is now given by the so-called confusion matrix. So if we now run that one, what you will see now is a typical example, which is given by the so-called confusion matrix. And in this specific case, what we have is a case now where we have either 0 and 1. So these are the outputs which we want to reproduce. And this is a true positive, and this is a true negative. So 0 means a benign tumor, so true positive. And then we have a true negative. This would be a false positive, it's a kind of false alarm. And this would be a false negative, which we again can think of as a false alarm. This is just one other way to classify the data which we have, and not to represent the data. So you can present it in terms of a true positive, true negative here. If one represents a malignant tumor, you have to define what is negative and positive output. And I would define, obviously, having a malignant tumor as a negative output, whereas a positive output is something which to me means having a benign tumor. And then you have true positive and true false. So there are very few cases which are misclassified, as you can see here. And this is a typical example of what you may get from logistic regression. If you tune this with neural networks and other methods, you will often see that you get a better reproduction of the data. And this is something which is at the basis of actually many of the more advanced algorithms for figuring out if a patient has a benign or not benign tumor. So a pathologist would typically go through all the scans and then say whether this tumor belongs to that or that class. But you can actually train based on all the data which are classified. You could then train models which then can be applied to data which has not been included in the training. And this is now routinely used in hospitals when they're analyzing cancer data, because it takes a lot of time to run through all the scans. So for complicated types of tumors, I mean, a pathologist and the medical team may use a day on a given amount of scans, whereas here you can actually run through all the scans in just seconds, and then flag the cases which are dubious, and let the pathologist and the medical team then go through the data and see if they would agree with what the machine learning algorithm has given. In that way, you can actually flag at a much with much shorter time what kind of tumor that patient, whether that's a benign or malignant tumor. Okay, so I'm going to stop the recording now, and what I wanted to say is that next time we meet on Sunday and Monday, we are now going to look at in more detail these different optimization methods, because they're really at the heart of all of machine learning. It sounds extremely simple. You're just tailor expanding your cost function. And then in order to find the optimal parameters, you retain terms up to second order. And that gives us, when we are looking at a practical scheme for finding the optimal parameters, due to the non-linearity in the dependencies, then we end up with a Newton-Raphson scheme, and that is the standard approach. But the problem is that we have to invert a matrix, and that matrix is given by the second derivative of the cost function, and this is something which is extremely expensive to evaluate numerically. And that leads to approximations which we will discuss in the next series of lectures.